Thank you for joining us on this math holiday. It's one of the few holidays that still's not overly commercialized. You know, they don't put out the Pi Day decorations when, you know, right after New Year's and all that kind of stuff you go through. And brought a piece of the furniture from our office here just to help with it. So I'm so proud of this thing. Yeah, you like that? I guess got to make sure. Thank you. I knew that nobody would say, get that out of here. We go. Pretty handy. So truly, pi is my favorite number. Years ago, probably talking, I don't know, maybe 25 years ago, there were a couple years where there was a faculty staff softball competition, and we made shirts. Jennifer, you played, didn't you? I'm thinking about it, and song it goes back. Tom, you played, right? John, one year, I think. Anyway, my number was pi even then. Okay, somebody else was like the square root of 2. We had fun with it, right? Infinity and all that kind of thing. But there's just something special about pi, and I know not just for me, but certainly goes back thousands of years that people were intrigued in pi. Sometimes it was just that pi was related to something they were very interested in, but a lot of times it's snowballed now to where there's a lot of interest in competitions, and it keeps growing that way. And as far as competition goes, at the end of the seminar, double check and see if there's anybody who wants to see, you know, like how many digits you can say from memory. And I have prizes. You would have your choice of, and we can have more than one winner, pi stickers. I love Amazon Prime, right? You need something like pi sticker, you go, they got it, right? Or even better, pi temporary tattoos, okay? And you get a whole strip, so you get all the colors that go with it. All right. And what actually first led me to the idea that maybe I'd actually want to do a seminar on the number pi was when I was reading this book. Here's Looking at Euclid, okay? It is so fun to read this book, written by somebody who's not only a mathematician but also a journalist. And so, you know, putting those skills together, the history and the mathematics combined, okay, there, and it has a chapter on pi and a lot of historical facts, etc. And I also had the book, The Joy of Pi, and so that has a lot of details. Sometimes they had conflicting dates for things. There's only one date I put on here with like an ish at the end, because it depends on who do you believe, and it give or take 3 years when it was a long time ago really wasn't important to me anyway. But these are the two sources for the majority of the information I'll be presenting today, and then some tidbits that I would find on other websites as we would go through. Okay, so my favorite number, pi. And so we'll just, you know, go back to what is pi. This is not going to be a big surprise to most of you. You know that if we go to the circumference of a circle, that the formula is 2 pi r. So pi is part of formulas like that. And since the diameter of the circle is twice as long as the radius, we could also say the circumference of a circle is pi times the diameter. Or that's just to be able to come up with, then when we divide both sides by the diameter, we've got that pi is the ratio of the circumference divided by the diameter. And I won't take the time right now to prove to you that if we had any size circle you want, that if we were to measure its circumference and then divide by its diameter, we always get, disregarding measuring errors, okay, we always get the same value, and that is pi. All right. And so today we'll look at some of it with math. A lot of it is history as we come through. So I thought I'd start out with, well, who named pi by the Greek letter pi? Okay? And actually, it's gone by this name only since 1706. Now, I know that was a long time ago, but people were working with that value, but not calling it pi. And a Welshman, William Jones, introduced the symbol pi in his book. Now, notice the title to his book. If I go by when it was listed, and here's looking at Euclid, we got a new introduction to the mathematics for the use of some friends who have neither leisure, convenience, or perhaps patience to search into so many different authors, turn over so many tedious volumes as is unavoidably required to make but tolerable progress in the mathematics. Now, other sources gave a much shorter name for that book. So I'm thinking that William Jones had a little bit of a sense of humor, and so on one part of it, for sake of his friends, okay, that might have, that was one of the titles that he gave. So that goes back to 1706. The symbol using pi to represent the value that we now call pi did not catch on. Okay, so everybody didn't go around calling it pi because William Jones did. About 30 years later, when Leonhard Euler really started using it as notation for that particular value, then it caught on and it stuck, okay? So go through with that. I would, probably should mention that William Jones, in this particular book, there were a couple places where he used the Greek letter pi, right, the lowercase p in the Greek alphabet, to represent different values, okay, just like he was using it in some other equations as pi. So he didn't just say, well, let's use this right now, only for that. So he had that habit. And from what I have read, when it stuck, probably part of the motivation in using pi as the letter is that it was short to represent periphery. So if you're thinking of like the circumference or, the periphery, the length around the outside edge, best guess on why they were using that Greek letter. But why wouldn't you want to use it? I mean, isn't this just the best, even of the Greek letters, isn't this the best one? I'm glad, I'm just checking to see how argumentative you are right now. It's good to know I got a friendly, audience here as we go through with it. Okay. And that picture, by the way, was Euler, okay? Just a little tiny picture that was there. Okay. Now, before they used pi, then what did they call it? Well, here we go. And if you can speak Latin, then go ahead and directly translate. But otherwise, it was most commonly known as kind of a clunky, the quantity which, when the diameter is multiplied by it, yields the circumference. Well, if you were going to discuss pi very much, that would be a pain, right? Just plain old be a pain, so much better to have some shorter name for it as they go through with it. All right. And as far as approximations for pi, the earliest approximations for pi came from two sources in general. Third one, some of Chinese sometimes get mentioned with this too, but the oldest ones normally it was saying Babylonians that used a value of 3 1/8, and there we look at 3.125. So it's in the neighborhood, right? Okay, and the Egyptians who used 4 times the square of 8/9. And that, instead of underestimating pi, it overestimates it a little bit, but still in the neighborhood. And rather than really trying to approximate pi, the Egyptians were interested in finding the relationship between the circle and the square. So it wasn't all focused just on pi itself. They're looking for that relationship. And the papyrus that they found they were representing it, where this came from. I mean, you can find the name of the Egyptian scribe that wrote it down, etc. He had written down that, well, if you take the diameter of a circle, cut off 1/9 of it, so you got 8/9 of the diameter, and then use that to represent the outside dimension for the length and the width of a square. Obviously, each square, everyone's the same, so it's all, every side is 8/9 of what the diameter of that circle is. That the area of the square is equal to the area of the circle. Well, it isn't truly equal, but if that were the case, this would be the value of what pi is. And it was close enough for what they needed, okay? When we're talking about these values, we work on them. Okay. Now, and those were going on well before even like 287 before Common Era time, okay? With the BC as we work through with it. Now, Archimedes used the method of exhaustion and found the perimeter of two polygons with a circle sandwiched between them, okay? To approximate the circumference. And this was something that other mathematicians were working with too. Often they were working with the area to then come back and figure out the value rather than where Archimedes was working with the perimeters. And because the circumference of a circle is pi times the diameter, if the diameter is 1, then the circumference of the circle would be whatever the value that pi is, okay? And of course, they weren't calling it pi at that time. They would have their own clunky long names, you know, as they would work through with it. Now, I will admit, in this particular diagram, this circumference is actually, it looks like they have the radius as 1, but I just want to show it to give the shape. So if the whole diameter was 1, then their circumference would be equal to pi. And just to emphasize that if you take one of those polygons, and he didn't always use the same one, okay? So you build up in the bigger one. That is, the circle touches it, so the circle's inscribed inside of it, okay? And then same shape polygon, but smaller, so that it's always inside the circle and just touching it. Then it makes sense that the circumference of that circle is going to be between the two values of the perimeters of those polygons. And so for this particular one, as that shows a thing with the hexagon there, that it would be between 3 and 3.46. Only makes sense that if you go with more sides, then your estimate is going to be closer to the real thing. We can see there's not as much error that would go through with that. And he went as far as to use polygons with 96 sides. Now, when Archimedes was working with this, he didn't start with like a square with 4 sides and then try to make a shape with 5 and then 6 and then 7 and then it was like doubling the number of sides that you have as you go through. And my understanding is he was working, using some formulas from Euclid, okay, to help shorten things up here. And I did not, my interest didn't take me into just going into all the detail that just Archimedes did, okay? But I mean, there were processes to shorten up what they were doing with it. But look at that, you've got to go to where you have 96 sides here, and that gave 2 decimal place accuracy. Here we get our 3.14, okay? Because whichever way you round those, rounding both of those, you still get the 3.14, which was probably plenty accurate for anything that Archimedes was concerned about building, okay? As we work through with that. Now, in China, all kinds of neat things were going on there. And look here now, 3rd century China. So we're now in Common Era time instead of instead of BC. Okay, and then that was new language to me. I guess I haven't investigated the BC and the AD compared to what they describe it with now. There's Chinese mathematicians. I won't even begin to pretend that I know how to pronounce their names correctly. Okay. but used again a similar method. Now that idea, of exhaustion is get closer and closer and closer and keep using more and more and more until you get the accuracy you want, using area of polygons with 3,072 sides. I did not look up to see, I don't remember when there's first record of use of an abacus. I should know that, but I don't remember that number. Because remember, whatever they're doing with their calculations, okay, they aren't using technology here as it goes through, but hey, look at that, go through, and it gave accuracy to 5 decimal places. Now, obviously, there was work done before this too, but I'm picking highlights as we go through. And if you only are going to be patient enough to wait 2 more centuries, okay, then another mathematician and his son went 1 more digit, okay, and using 12,288 sides, okay, to these polygons that they were working with. So we've got 3.141592. Now the Greeks with Archimedes and the Chinese were hindered by cumbersome methods that they had to use for notation. And when mathematicians were able to start using Arabic numerals, that really, really sped things up. So I know when I was looking through the history and when did the use of Arabic numerals spread to Europe, we're looking at like the 1200s. Okay, so that was way after this, and they weren't using certainly any of that in that point. So if we go past that, here's a few hundred years after the use of Arabic numerals became more common in Europe. And I like this, a Dutch fencing master. See, math is like that, right? Any place you are in life, there can be some parts of math that just grab you. Some people won't admit it, but at some point, there's that was actually kind of interesting. Well, here's this fencing master, Ludolf, I think it's Van Quellen, I could be pronouncing that incorrectly, but he used a polygon of 60 times 2 to the 29th sides. Now, he wasn't drawing them, working with the formulas. And by the way, that's a pretty big number. It seems like, let me calculate that. It's just a little over 32 billion. Okay, so, all right. And he found 20 decimal places, right, do that. And it says in a pamphlet that he made about his results, he ended it with the words, "Whoever wants to can come closer." Right? He was worn out, but proud of his work, I think, by then. However, he himself, he eventually was able to calculate 32 and then 35 decimal places, and those numbers are put on his tombstone, right? So I didn't say anything about if the number of fencing matches he won was put on his tombstone. What mattered, right, was how many digits of pi was he able to work with on that. And his name is actually, this is in German, is still sometimes used to indicate that you're talking about the number pi. Now, for about 2,000 years, using polygons was the only way that they were able to look for more and more decimal places. I mean, it was the challenge that would go through with that. And then some other things that were happening in mathematics started to really help. Now with Gottfried Leibniz and John Gregory, not working together on it, doing their own thing, but they were 2 mathematicians that helped really make a difference as they're applying using series, now infinite series. And so this is really representing the same thing, but one with a summation notation, and then the values you would get out okay, written on top as you go through with it that way. And those formulas were extremely helpful as they were doing calculations then to find pi. And obviously, okay, that's pi over 4. All I want to do is say, let's just multiply both sides by 4. And we got a nice clean pi equal, right? Easy to do, and that's what can happen with it. All right. However, this formula, okay, calling that infinite series a formula right now, requires more than 300 terms to get an answer for pi accurate to 2 decimal places. So it's a way to maybe show a really elegant path and how to get there compared to the polynomials. But you still, I mean, there's a lot of computations to be making here with it. And this, you know, I ran into, you know, the opinions are, it really converges too slowly to be real practical at the time. They keep finding lots of digits. But it's cool, it is really cool. You know, back then, again, they didn't have something to be speeding this stuff up as they work on it. And so, as time went on, there were additional infinite series that people devised to represent what pi is, okay? They weren't as pretty as the last ones, but some of them were better for number crunching if you're actually having to find those terms. So in 1705, an astronomer, Abraham Sharp, used a series to calculate pi to 72 decimal places. Now, there are records of an incredible number of people who've been working on finding the values for pi, and I picked some names to pull out. Okay, I'm going to be leaving out some incredible work that was done, but there, you don't need me to list like 100 things right now as we go through. So look at that. You went 72 decimal places. That's 1705, all right? And that's pretty interesting. However, for the practicality of it, so there's no reason to know that 72 decimal places, because 10 decimal places is enough to calculate the circumference of the Earth to within a fraction of a centimeter. So it's not about like building things and all of that, but it's more just for the beauty of the number itself, okay? And the challenge, right? The challenge to do it as you go through. And this might be stretching things, but picture a track meet in the Olympics. And the point of people running the 100-yard dash to see who gets the best time isn't because we depend upon people running real fast 100 yards to get things done right now in this world, right? But it's still like, how fast can you get it? So, and I watch the Olympics and I appreciate what people are doing. So just an example. So here, some of that, just a reward in itself to find those digits. In 1767-ish, I found a couple of different dates, but still within that neighborhood, Swiss mathematician Lambert proved that pi is an irrational number. And of course the important part there is that, oh wow, we don't have to worry. There's no disappointment in, oh, we just found the last number. What else is there to do? It'd be a little bit like the old man in the sea catching the biggest fish, and then what are you going to do? So there's no problem with that. Right? It's irrational. Those decimal places don't fall into a repeating pattern, and they do not stop. All right. And here are just some examples, pulling it out. So I mentioned the 1705 there for Abraham Sharp. 1706, look at that, went up to 100 decimal places. And I purposely was picking, these are people from different countries, et cetera, as we would go through. So it isn't just happening in one country. All right. 1717, up to 127. I can't imagine the work it takes for every digit that comes through with that. 1794, 140. And then, another big leap, 1844. A nice round 200 digits. All right? And then in 1853, William Shanks. Look at that. He's an amateur mathematician who ran a boarding school. Now, what do you suppose those students did during math class? Do you think, you think he maybe had some like power but scribes? There you go. Oh, man. So, in 1874, he found 707. Isn't that amazing? But, oh no. His record held for 70 years until D.F. Ferguson of the British Royal Naval College found a mistake in the calculations at the 527th place. I'm thinking that by then William Shanks wasn't around to know about it, so maybe that's just as well, okay, at that point. And it meant then that all the digits following it were wrong, because in this series where you're adding them together, right, that mistake made all the others wrong. But Ferguson kept working on this in that college. I tried to find more about him because of all the math he was doing during World War II. And I was just kind of curious as to, at that time, as much as I love pi, why he was focused on that. I actually could not get more information about why that's where his energies were directed during the war. But he was calculating this longhand, right? No technology to go with it that way. By May 1945, okay, he had 530 places. Well, so it took a lot of work. First of all, he had to find a mistake. Isn't that interesting? So these people who are these fact checkers, right, to go through. Then by July 1946, he got to 620. And that record, from what I could see, still holds for if you're doing it by hand, pencil, paper stuff, because he got a calculator, right, to go through with that. He was the first to use the mechanical approach, and he was using a desk calculator. I would love to see in the 1940s, what his desk calculator looked like with that. But then he added almost 200 more places in just over a year, because he had something that could really speed up things as you go through. And I know before that, obviously, they had the advantage of things like slide rules or whatever, but you ask John Dersch, I've told who, he's wondering what are you going to ask me, but as far as my affection for slide rules, I'm really trying to give them, having the nostalgia come back and have affection for them. But when I used the slide rule in high school, my slide rule was not my friend. If you don't have that lined up just right, or supposedly if it's a humid day, right, you just, the errors that can come in with something like that.
Well, I can give you some evidence of how much Nancy loved her slide rule, because she gave me for some
I did. And just for history's sake, I had wonderful parents, and even though I was number 5 of the kids, they still, when my math teacher told me, hey, she knows her math, you should get her a really good slide rule. They got me this beautiful Pickett slide rule. It was about this thick, and it came in a case, and it's like you're supposed to put it on your belt, as if I was going to go down a high school hallway with a slide rule on my belt. No, you hid it. You hid it in something back then. Some of you are from my generation. You didn't have book packs. You didn't even have Trapper Keeper things. You just had a notebook that opened, that you hid it until in math class it was okay. Then you hid it when you went back. Oh, goodness. Yeah. All right. And computers, of course, change things even more greatly than being able to have a desk calculator. Now, so the race is on, and now that computers are being used, by the 1970s or during the 70s, the record of digits was about 1 million. But I mean, 1 million is an awfully big number, right? When we're looking at how they just clawed, right, for all that work they did in order to get to another digit. And then in the 1980s, there was a race between the US and Japan. I mean, and part of that is the competition with the computers as we go through, but in particular the competition with those two countries. And we're talking hundreds of millions of digits that they could get. And one country, by that, the mathematicians and computer scientists are in there would do it, and then sometimes just a few days later, right, the other country could increase it, et cetera. And then in the United States, out of the spotlight, Ukrainian-born mathematicians, these brothers, Gregory and David Chudnovsky, came up with a new formula, a new series that they use for calculating pi. Okay, because what's happening here with pi being the irrational number, not only is it just for the fun of it to find the digits, but it's becoming a way to test the processing speeds, et cetera, of computers. But they came up with a new formula. So if they're using a different series, okay, in order to get to the number, that would affect things. And in the 1990s, they built a supercomputer in Gregory's Manhattan apartment out of mail order parts. Now, they still spent thousands of dollars on this thing, but it compared to if they had bought something comparable, okay, they were able to save a lot of money. Otherwise, they wouldn't have been able to afford that. And using their own formula, calculated pi to more than 2 billion decimal places. Now, before they built their supercomputer, but they had their formula, what happened is they could get some things running, but on a smaller computer, it just would be so slow. Okay, it would be kind of crazy that way. Some records that come into play, when I would read some of the records that are out there and how many digits somebody found, sometimes they were done by just little tabletop PCs, and it would say, how many weeks or months the thing had to run. Okay, but before they built this, they had arrangements with some of the sites in the country that had supercomputers, and you could have use of their processing capabilities on like weekends and holidays and in the middle of the night, and you hooked up over phone lines. But so they did some of their work to start with that way, but then they came to the conclusion we need our own computer. Right? So it's in their apartment, and if you have seen the movie entitled Pi, it was based on an article about those brothers, the article that was in the New Yorker, okay? To put a little bit of history in with that. Now, this supercomputer had to be huge. And they kept it on all the time because they were afraid that if they turned it off, it wouldn't start again. So, and it needed 25 fans to keep it cool, because these things, what they had to make them with generated an incredible amount of heat. Now, they've changed that a lot with computers. Do you remember the older desktop computers where you could, the sound of the fan running inside them to help keep them cooler was quite noticeable, et cetera. So that's changed so much, but boy, back then, the heat was something else. And they were careful not to turn on too many lights in case it blew a fuse. they're totally dedicated to mathematics. And finding how many digits of pi they could get is a great challenge too. But willing to minimize the number of lights on. They were careful. I think they went to a laundromat because who's going to dare, turn on the washing machine and all that type of thing. So there's the brothers in their, earlier years. And the brothers, when I was reading an interview with them, they said, well, after we'd been computing pi, we got a phone call from the United States government, and they said, can you send pi? Okay, and what they meant is the number, because industry and commerce need random numbers, and the distribution of the digits is 0 through 9, okay, as you work through pi, it's so beautifully randomly distributed. I did see some information in my readings about some people would take the first, I don't know how many thousand digits of pi and try to find out if it's a normal distribution, and it looks pretty good. I don't even remember which digit. One of the digits is off just a little compared to the others, but it is, even though they're randomly distributed, where they show up, it tends to be a pretty even amount of time. And so, in all seriousness, the government, wanted to know what what that formula is, or probably more likely than that, just wanted the number out as far as they could do it for that. And I thought, well, in case you were interested to see what series they used, this again piqued my interest. It's 1 over pi instead of pi equals. So this series is actually like the reciprocal. That doesn't bother me for some reason. As you go ahead and work with that, then I just like to think of that, that's all right, that's just 1 over that series. You got a fraction with a little series representing what the value of that denominator is going to be. But notice how it's got factorials in it, as you would go through, and a computer can run through something like that. And it seemed to run faster than what they tended to use previously. Because when I was looking at following them, like what some of the records were that came through, you can find websites where it will say, well, on this date, this is how many digits they got to, and it was a whole bunch of them referring to they were using this. So I didn't see anything where somebody feels like right now they have a series that could be used to generate it faster and easier. Not to say it's not out there, but in my short search, I wasn't seeing evidence of that. Okay. Now, finding digits of pi is a great way to test certainly the processing capacity of computers. But again, because of the beauty of it, and because we all know math is cheap entertainment. I mean, it's more than just to get something done, right? It's just some cheap entertainment. At least that's my motto in life. Look at some of the competitions that they have. Probably not a surprise to you. Some people memorize the digits of pi, right? And they have competitions where you can do that. I love pi, but I haven't made an effort to see how many digits I can memorize, because to me, memorizing a bunch of stuff has never been important to me, okay? I can appreciate pi here, and without doing that. But the people who can do that, remember, have my admiration. So I'm not trying to belittle what they've done, but for me, that's not how I spend my time. Now, that's not enough of a challenge for some people. There are competitions where you are reciting pi while you're juggling, right? And if you want to try it, I got these. I'm not going to juggle right now. I did buy a book once. I couldn't find the book right now. It was just one of those dummy books. So it was Juggling for Dummies. I thought for sure that if I could get juggling down, there'd be all kinds of applications in my classroom to have an excuse for me to juggle and amaze them. I could never get past the 5th toss, but my cats loved it when I was practicing. Okay, just, you know, sometimes you just say, save it for the future. Okay, it was one of two things that got the best of me. Also, when I tried to learn how to ride a unicycle when I was a kid. Now, if we had a sidewalk longer than 6 feet, I might have gotten it down. But we lived in the middle of nowhere, so, you know, so I had to give up on that one too. All right, but people do this, and I'll give you some numbers in a minute, okay? Or how about the Everest test? They take the first 10,000 digits of pi's decimal places, okay? So we're just not using the 3 at the beginning. And then put it in groups of 5 numbers. So you got 2,000 of those groups of 5 numbers, right? And, okay, and then out of this 2,000 groups, if you're in this competition, they pick 50 out of them randomly, probably using pi to figure out which one. 50 of those. And so they'll read the 5 numbers, and then the person in the competition has to be able to say the 5 digits that would precede it and the 5 that would come after it, right? In order to be able to do that. And that's with 50 of them. Look at this, only 4 people in the world. Now, when I looked at, who knows, maybe yesterday somebody broke a record, right? But when I was looking, 4 people in the world can do this with no errors. And Mats Bergsten, an actuary in Sweden, has the fastest time, 17 minutes and 39 seconds to do it. So it's not like you can, if you learn it to a song or something, you can't, you know, sit there and re-sing the song for 20 minutes for every single one. And not only that, with the Everest test, look at that. He also recited 9,778 digits while juggling with 3 balls. So, no, there you go, right. Or he would have had off. But you see, who knows? Maybe he just dropped the ball. Might not. Start again. 1, 2, 4. Oh man. All right. Okay. Now those. There's this. You get 3.141592. Kind of. Should I improve my penmanship there? I'm writing out pi, okay, but I didn't put the decimal point down there. But how about creating a phrase in which the number of letters in each word represents each consecutive digit in the decimal expansion? So here people's creativity come into play, not just memorizing it. So a well-known English one. Now when the source said well-known, that might be relative. I don't know how many people did. English one, who was astrophysicist Sir James Jeans, is how I need a drink, right? So there's your 3.141. Alcoholic in nature, after the heavy lectures involving quantum mechanics, all of thy geometry, Herr Planck, is fairly hard, right? And so there's an example of one to bring it out this far. And I was, writing above those because I wanted to make sure my source was correct. And sure enough, there's the digits for pi. And then poems that are written in that same format, so-called poems, right? And a 0 gets represented with a word with 10 letters in it. because you know, how else would you represent 0? And this is just the beginning of one, but look, it actually follows pi for 3,835 digits. So it's a very long poem. And this is the only part that was being displayed at the time. But that's pretty tricky stuff as we go through, I think. And in the two books that I used here, here's looking at Euclid, which there's a few parts of it I still need to read, not the parts about pi, but there's a chapter or two I haven't written yet, but read yet. But it's, to me, just fascinating reading, because now I love mathematics, but I love story and I love history. Probably the reason I like history is because history is just story, right? All the things that happen. And I recommend this book for if you're interested in pi, but a lot of other things too. Stuff that's going on right now is gone to the Amazon jungle. It goes to different villages where they count using different bases. Their number systems, having been isolated, totally different. It might be base 6. They never needed a number bigger than 20, because if there's more than 20 wolves, you just run, right? I mean, there was no, I mean, there's just the math that's in there too. And there's lots of history and tidbits in here, but it's more a bunch of facts without the story that wraps around it. Well, thank you very much. I hope you have the rest of your Pi Day is festive and stress-free. Help yourself to more cookies.